And this speaker, our first plenary speaker, is Professor Nicolas Gisin from the University of Geneva, who is distinguished, among other things. I think I'm right in saying this is the first recipient of the John Stuart Bell Prize. Professor Gisin is going to be talking to us on quantum correlations in Newtonian space-time, faster than light communication and non-locality. Nicolas, welcome to Trinity.
Thank you. Thank you. Well, thank you very much for inviting me here, so I can see that the weather is always so beautiful in Cambridge, and I don't understand why the locals always want to go to Côte d'Azur. Especially thank you for inviting me, although I'm not going to talk about retrocausation. Actually, what I want to tell you about is a failure of trying to explain these strange quantum correlations that we already heard about, those that violate the Bell inequalities, to explain them with the idea that there is a direct cause from Alice to Bob. So Alice does something, and there is something going from Alice to Bob, and I will call that a hidden influence going from Alice to Bob. So it's a very natural idea that there is something going from Alice to Bob. And that has already been tested experimentally by, and usually it is also presented that way, that you should have Alice and Bob space-like separated so that nothing going at the speed of light or slower than the speed of light can connect them. But what about the idea that there is something that goes from Alice to Bob faster than the speed of light? That would be very natural, but because it goes faster than the speed of light, it is certainly not in the spirit of relativity. That's why I'm talking here of quantum correlations in a Newtonian space time. So all the motivation comes from this violation of the Bell inequality. Because indeed from this, because of this, we face a tremendous challenge to just tell a story of how things happen in nature. You can say it goes backwards in time with retrocausation, or I don't know, you say it all happens in configuration space and we only see the shadow of this configuration space, or I don't know. I mean, of course, Lev is going to say it happens in the multiverse, but all that is not a very clear and satisfactory picture. And it would be much nicer somehow if we could say, well, there is simply Alice who is influencing Bob, maybe at a billion times the speed of light, but at some finite speed. So the idea is that it goes, continuously and gradually through space as time passes. And in order to have such a picture, one needs a universal privileged reference frame. And so in this hypothetical universe privileged reference frame, then I can tell a story also in Newtonian space. Okay, that was the program that I started many, many years ago with all these collaborators, Jean-Daniel Bancal, Stefano Pirogno, Antonio Assin, Yongchen Liang, and mostly actually with Valerio Scherani years ago. Okay, so let's also to motivate that, go back to some other kind of non-locality that we all know about. We know about Newton's universal law of gravitation, or law of universal gravitation. And according to this law, if a stone is moved on the moon, that would have an immediate effect on the gravitational field on Earth. And the fact that it would be immediate, that's the non-locality. You change something there and it has an immediate effect there without anything propagating and carrying that effect. And so how could these two locations out there in space-time know about each other? And I think this is a very natural and good question, and I'm in good company. Sorry for that. Yeah, of course, since this is all physics, we should have done the experiment. Of course, at Newton's time, it was not possible to do the experiment. Even today, it is not possible to do this experiment because, moving a rock on the moon is technically possible today, but the effect on Earth would be too small, and you would have to make this measurement over very quickly, less than a second, so less than the time light to propagate here, or actually for a gravitational field to propagate. So one cannot do it. But still, if you would, if someone really does this Gedanken experiment, he would have first falsified Newton's theory, finding out that actually it takes some time to propagate, it's not instantaneous. And yeah, that's what I'm saying here. Now that this kind of non-locality is shocking was already well known to Newton, who himself wrote that, maybe he was just across the street here, I'm not exactly sure. He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which the action and force may be conveyed from one to another, is to me, so to Newton, so great an absurdity that I believe no man who has in philosophical matter a competent faculty of thinking can ever fall into it. So essentially Newton was telling us, you have to be mad to believe in my theory. And it is interesting that, I mean, despite of that, during more than 3 centuries, this was the prevailing theory. I don't really understand how physicists could accept that during centuries. Probably there is some story, and maybe some philosopher or historian can tell me more about that. But also, I mean, that's still what we teach our students, no? I mean, our students should jump up when we teach that. They should never accept that. By the way, when I heard that and I was a high school student, I accepted it because I respect my professors. But it was absurd to accept that. You know? Okay, anyway, so are we facing the similar kind of situation with quantum? So in order to come to that, let me be a bit more precise. So to send information, one has to encode it into some physical support and send this physical support to the receiver. That's one way of understanding this famous Landauer's statement, according to which information is physical. You cannot sort of send information abstractly. You have to encode it into something, and that something goes from the sender to the receiver. And any other way of communicating would be something I call signaling. So signaling here just means it's non-physical communication. It's communication without any physical support. Or it's telepathy, if you like. I don't know if you are, okay, what you understand by telepathy. But let's use the word signaling. It's more neutral. Now also, if you could do signaling, then the distance doesn't matter. It's like in Newton's universal gravitation theory. The distance doesn't matter at all. So because the distance doesn't matter, you could also, if you could signal, you could also communicate faster than light. And that's the usual way of presenting signaling, is faster than light communication. But I think that signaling is actually much more fundamental than no faster than light communication. So, okay, I'm willing to consider, at least in the coming hour, faster than light communication, but I'm not willing to consider signaling, not willing to consider communication without any physical support. And that leads, I think, to the principle of continuity, which states that everything, be it mass, energy, information, propagates gradually and continuously through space as time passes. So nothing jumps instantaneously from here to there. There is no instantaneous teleportation. In quantum teleportation, there is also some classical communication, so it is not instantaneous. And from that, you deduce that correlations, all possible correlations, can have only 2 types of explanations. It's either a common local cause or a direct cause, which here I will name influences at finite speed. So the common cause, you know, from this space-time diagram, that is well known, and actually, of course, influences at finite speed is also something very well known. It's direct causation. Now, on the common cause, you all know all these arguments by Bell and Bell theorem and experiments and all so on. So let's say this is a falsified explanation. So I want to concentrate on this line here. So a direct cause explanation with influences, and I'll say more why I say hidden influences, but already, let me emphasize, at finite speed. So if we would have that, so Alice does her measurement, then there is this hidden influence going to Bob, and then Bob makes his measurement, and of course this result now can depend not only on the input, maybe on some initial state, this lambda here, but can also depend on Alice's choice because there was time for this hidden influence. Now how would you test such an assumption? Well, very naturally you would try to ask the two questions at the same time. And in this way, the result on Bob can only depend on Bob's inputs or Bob's measurement settings, of course on the state, but not on anything coming from Alice because there is no time for it. Remember, this hidden influence goes at finite speed, so it will take some time to arrive. And in this case, we'll fall back to Bell locality. That's the only source or only local common cause can explain the correlation. Now these faster than light influences need to be defined in a hypothetical universal privileged reference frame. And as I already said, this is not in the spirit of relativity, but is also not in contradiction to relativity. For instance, they exist, and we know it, we know how to characterize it very well, a frame in which the cosmic background radiation is isotropic. For instance, we know that Earth is moving with respect to this privileged reference frame at, I think it's 379 or 69 kilometers per second. I mean, there's a very well quantified number, and also in which direction we are moving is all very well known. And you can find that on some websites. So there exists, at least this is one example, and of course there could exist some other example of these privileged reference frames. So now once you have this, you can go and make experiments, and so here we did some experiments between, so this is Lake Geneva, and so there are two cities, east and west of Geneva. I don't want to go into the detail of the experiments, but okay, we did experiments, so this is our experiment, then some Italian did also some experiments, and more recently a Chinese group did also this kind of experiments, so trying to do this measurement really at the same time as that one, and then of course you may ask in which reference frame, and I don't want to explain that here, but if you want I can tell you, well, either during coffee break or afterwards. And so in this way you can get some bound, because of course you will never be able to be exactly at the same time. Everything is within experimental uncertainty, so you have only a certain precision with your timing. And because of this finite precision in the timing, if the hidden influence really propagates extremely fast, it would still arrive within time. So all what you can do experimentally is to set a lower bound on this hypothetical, on the speed of this hypothetical hidden influence. And from these experiments, of course, you can make nice publications. That is already very good, especially for the students. But what can you really conclude out of that? Well, of course, you may just say, oh, the influence is merely propagating faster. So I have only put a lower bound, it could go faster. Of course, it may also be that nothing like that exists. And if you think more, you see that with two parties, so if you just have Alice and Bob, and you do better and better experiments, okay, you can improve this lower bound, but you will never really be able to exclude hidden influences. Of course, what would be superb is to find a situation where the quantum correlation disappears. But as long as you continue violating Bell inequalities, all what you do is to maybe improve this lower bound. And so as long as you have only two parties, you cannot use this kind of hypothetical influence to communicate. Because all what you could do is, let's say, Bob moves a bit away or does not move away so that the hidden influence arrives on time or does not arrive on time, things like that. But I mean, the local statistics of the results would not change at all in these two cases. Now, whether the results the correlation are the usual quantum correlation, or whether the correlation are just those corresponding to a product state, locally, the local statistics are the same. So there is no way to communicate with this kind of hypothetical hidden influence. And that's why I say that they are hidden, because you cannot communicate using them. At least you cannot communicate using them just by looking at the statistics of the classical outcome of your measurements. And as long as you have only two parties, they could remain hidden. So you can still think that this is a good explanation, as long as you have only two parties. And indeed, that's actually the way that many people, including famous people, were thinking about it. For instance, John Bell used to say that something is going on behind the scene. It's exactly this idea. There is something hidden that is going on behind the scene. We don't see it, but that's the mechanism that explains these strange correlations. Also, David Bohm, together with his co-author Basil Hille, was very explicit. It is quite possible that quantum non-local connection might be propagated not at infinite speed, but at speeds very much greater than that of light. In this case, we could expect observable deviations from the predictions of current quantum theory. So David Bohm was also very much aware that, of course, in his model, as you probably all know, the non-locality, or this quantum potential, changes instantaneously, also in Newton's universal gravitational theory. But Bohm was saying, maybe it doesn't go instantaneously, maybe it goes at some huge but finite speed, and we should look at that. Moreover, also, if you read any non-relativistic textbook, you also get these kind of stories. I mean, a first measurement collapses the entire wave function, hence changes or influences the state of all the systems entangled with the measured system. Well, this is the typical kind of sentence you can read in these books, in which I learned, and probably most of you also learned quantum physics. So we learn actually quantum physics telling this kind of story. That's something you do here, somehow, I don't know, jumps or propagates there and has an influence there. So let's try to make that more formal and see how we can analyze that. So we're going to assume that there is this hidden influence that propagates at a speed, and the only assumption I make on this speed, it is not infinite. So it really propagates, because, it can be larger than c. And whenever an event happens, a measurement produces some result, the rest of the universe is informed at that speed v. And whenever this hidden influence arrives on time, future events are correlated as predicted by quantum mechanics. That's all the idea now. If this hidden influence arrives there, then of course the later event will take that information into account. However, whenever the hidden influence doesn't arrive on time, events can only be Bell local correlated, so only correlated via common local causes. So important here is that in V-causal models, predictions may differ from quantum theory. And this is why this is really different from Bohm. Now, in Bohm's theory, V is infinite. And if V is infinite, the hidden influence, or this change in the vector potential, in the quantum potential, always is on time, because it's immediate. Always on time. And now to motivate you to continue listening, is that I like to present you an argument, which will again be based on some inequality, that shall prove that hidden influences at finite speed leads to signaling at the macroscopic level. So if you don't believe in signaling, so if you don't believe in telepathy somehow, then you have to abandon V-causality. So again, what is V-causality? So in blue you have the usual light cone, now drawn in this privileged reference frame. So this is time and this is space. And so in this privileged reference frame you now also have a V-cone. In case here V is larger than C. And clearly these two events, they are I will say connected or V-connected, so there is time for this hidden influence to go from here to here, but not between these two events. These are not connected. Okay, yeah, here I just want to give you some intuition, because at the end I'm going to tell you, to present you a theorem, and okay, it's mathematically correct, but maybe it doesn't give too much intuition. Why should this finite speed hidden influence allow one to signal? So let's assume that we have three parties, Alice, Bob, and Charlie, and they share 3 qubits in this GHZ state, 0, 0, 0, plus 1, 1, 1. And make now also the additional assumption, which I will remove afterwards, but just for the intuition, to make the intuition a bit clear, that there are no local variables. So there is nothing more. The state of the universe is really described only by these states here. There is no lambda, no additional shared randomness. So in this case, you can do the following. You can arrange that Bob and Charlie are perfectly well synchronized. Let's say they are a kilometer away and perfectly well synchronized, so well synchronized that there is no time for this hypothetical hidden influence to go between Bob and Charlie. Okay? However, Alice is far away, a light year away. She's really far away. And then there are two possibilities. First, Alice does nothing, doesn't do any measurement. Easy to do. And in this case, because Bob and Charlie, they are not connected, not V-connected, they cannot correlate. Remember, there is no local variable, no local hidden variable. And that means that Bob and Charlie's outcome are independent. You know, for Bob, he has just 50% probability at 0 with 50% at 1. Sorry, I forgot to say, they measure in the Z basis, so in the computational basis. So he will get 0 or 1, 50-50 cases, and the same for Charlie. And there is no correlation between them because this hidden influence does not arrive on time. So they get uncorrelated outcomes. So outcomes are independent. However, let's suppose that Alice does the measurement first in this privileged reference frame, and in such a way that there is time for this hidden influence to go from Alice to Bob, and then of course also from Alice to Charlie. Now Alice will get a random result, but this hidden influence will correlate Alice and Bob, and will also correlate Alice and Charlie, in such a way that now Bob and Charlie are correlated. So you see that by Alice doing or not doing her measurement, performing or not performing a measurement, changes the statistics between Bob and Charlie. Of course, it will take, I don't know, a millisecond for Bob and Charlie to communicate whether they have correlations or not. But a millisecond compared to this light year here implies that they can communicate much faster than the speed of light. They can actually communicate essentially at the speed of this hypothetical hidden influence. So this is the assumption, that's the intuition. But of course, in this presentation, I made the assumption that there are no local variables. So this is the obvious and the immediate objection to this kind of picture or example. And so now I want to be able to combine hidden influences at finite speed plus local variables. So let's look at this situation. And I need more than 2 parties. And I will use 4 parties. I'll say something about 3 parties later, but why not have 4 parties? It's not yet an enormous number. So I have Alice, and Alice will be, again, in this privileged reference frame, time and space. Alice is first performing her measurement. And the arrangement is such that Dave will be second, and Dave is connected to Alice, you see? He is inside Alice's V-cone. And in the future of Dave, there are Bob and Charlie. So Bob and Charlie are also connected to Dave and to Alice. However, Bob and Charlie, they are not connected. And because they are not connected, the correlation between Bob and Charlie must be local, in the sense of Bell. And they must be local, whatever Alice and Dave did in the past. Their correlation has to be local. On the other side, because Alice, Dave, and Bob are connected, the ABD correlation, so the correlation between Alice, Bob, and Dave, that must be quantum, because here the hidden influence arrives on time. And the same for ACD, also arrives on time. Okay. Now we go to a special case where the inputs, so the Alice, Bob, Charlie, and Dave, they have a choice between two possible measurement settings, very similar to the CHSH Bell inequality, and also the outcomes are binary. So the inputs are labeled 0, 1, and the outcome plus or minus 1. And then there is a theorem which says that if this joint four-party correlation, so the probability that Alice, Bob, Charlie, and Dave get output A, B, C whenever their measurement setting is X, Y, Z, and W, if this is non-signaling, and if the marginal BC is local, again, local in Bell sense, whatever Alice and Dave did, then a certain inequality holds. G is smaller or equal to 7. Well, this inequality G is what is written here. Now, to find this inequality was a tremendous challenge. It's not something that you can find like that over the evening or the weekend, not even. It's an enormous challenge. I can tell you more how technically you do these kind of things. I mean, you go to huge polytopes and you need students like Jean-Daniel Bancal and Stefano Pirogno to be able to do this kind of stuff. But once you have the inequality, to prove that this inequality indeed follows from these assumptions, this is pretty trivial. So the difficulty is to find it, but once you have it, it's a few lines of elementary algebra. So the demonstration of that is a bit more complicated than CHSH, but not much more. I don't want to do it here, but believe me, it's easy to prove. It's difficult to find, but easy to prove. Now, if you look at all that, and all these, I don't remember how many terms there are here in, there's one thing which is remarkable. Here you have no terms which will involve at the same time Bob and Charlie. Bob will appear somewhere, for instance, A, B here. Charlie appears, for instance, with an AC here. You may also have A, B, D here, and A, C, D here. But B and C never appear in any of these expressions. And that is of a tremendous value, because it means that if you try to do this kind of experiment, you don't need, if I come back here, the difficulty would again be to make sure that these two are not V-connected. But you don't need any longer to make sure that they are not V-connected, because in the experiment, sometimes you measure A, D, and B, and you just forget about C. And sometimes you measure A, D, and C, and you forget about B. So there is no timing issue between B and C, because the inequality does not involve B and C. It is strange that you can use the fact that BC is non-local, although you never measure BC jointly. But we know in probability theory that we can often say a lot about a joint probability theory for marginals. And that's exactly what we're doing here. We are only using marginals to infer something about the global probability distribution. Now,
so this means something like the average value that at station A we get the number 0? Is that the first term?
Depends on the state. If it would be the GHG state, yes. But it depends on which is the quantum state, of course. If you have a state where the marginal Alice is half the identity, then indeed that average value would be 0.
So if C is inside the light cone of this risk cone of B, the J still should fulfill this?
No. Well, then no. Here we make the assumption that BC is local. Now, of course, if C would be in the future of B, in the V future of B, then this assumption, well, you can still make it, but this assumption would not be a natural assumption. In this configuration, it is natural to assume that B and C are local, because they are not connected.
So then, why it's important that you don't really measure BC?
Because
there is B and there is C.
On the theory side, I can just say BC are simultaneous. That's easy to say. But if I do an experiment, how can I make sure that BC are really simultaneous? You know, I will have some experimental uncertainty on my measurement time, and then I get in the same trouble I had with these experiments I did some years ago. Here, the fact that I don't need to measure BC at the same time, I don't need actually to synchronize BC.
Sorry, that in every run, what do you measure?
Well, we did not the experiment, so it's still on the theory side. But if we do the experiment, sometimes, for instance, here we need to measure Alice, Bob, and Dave. Here it's Alice, Charlie, and Dave. But you see, you never need to measure Bob and Charlie in the same run of the experiment. So there is no term that involves B and C. There are all the other possibilities, but not that one. Okay, and now also because there is no BC, any V causal model will predict the same value for this J here as quantum mechanics. Because all the terms that appear here are between connected events. And all the connected events, by the assumption of V causality, make the same prediction as quantum mechanics. So although I don't know this hypothetical V causal model, I know that the V causal model for this specific value, J, will make the same prediction as quantum. It may make different predictions for different experiments, but for this experiment it's going to make the same prediction. So I can make a prediction for V causal model without knowing this V causal model. And that's what I think. V causal prediction differ from quantum, but since J doesn't contain any term involving B and C, the V causal prediction for J is merely the quantum value. Okay, we just said that. Okay, now from that theorem, okay, now you need, of course, the theorem is interesting only because there are some quantum states and some quantum measurements that predict a violation. That's like for Bell inequality. Bell inequality wouldn't be interesting if you couldn't violate it. Same here. And then, because you can violate this theorem, so there you can read it in two ways. You could say that if you assume no signaling, you could, from a violation, conclude that BC has to be non-local. So this is surprising in itself. It's not really the point I want to make here, but maybe it's interesting to say also that you can actually conclude about non-locality between two parties, okay, Bob and Charlie in this case, without ever measuring them simultaneously. It's always surprising, it's counterintuitive. Of course, it's actually not really new. This is the kind of thing that exists in also in classical probability theory. But I want to go the opposite way. Actually, in a V causal model, BC are necessarily local. And so a violation has to be interpreted as saying that ABCD must be signaling. So from a violation here, I conclude signaling in any V causal model. Now here, signaling doesn't really mean signaling in the sense that I presented earlier, this non-physical communication, because the assumption here is that there is something going from Alice to Bob. There is this hidden influence that could be carrying this message afterward. But it would be faster than light. But now let's see even that this faster than light, where is it? It's not coming
Sorry. So in the statement of the theorem, if non-signaling means what we used to call parameter independent.
Yes,
it
yes.
Also, okay.
Yeah, exactly.
So this
Exactly.
corresponds to your finding.
Yeah, I wanted to find this. Exactly. So this here technically means that if I trace out any of these four variables, let's say the last one, D, then the result would not depend on the last input, on the last parameter. So it's exactly parameter independence. Non-signaling is parameter independence. Well, that's what I said before. You could deduce non-locality. Okay, so what I did so far, just on the theory side, so this is what we said before, is Bell theorem. Now I have an argument saying also that if I have finite speed, I get a contradiction with no faster than light. But I think there's one slide that is missing. Okay. Let me find this slide because it's an important one. Yeah, this one is missing here. I don't know why. Too many versions, and at the end something is missing. So far we have this parameter dependence, but I want now to prove that this parameter dependence can be used to really communicate faster than the speed of light. So now we could of course think we trace out Bob. But if we trace out Bob, we end up with Alice, Charlie, and Dave, but they share quantum correlations. And quantum correlations don't allow you to communicate. The same if I trace out Charlie. So the only interesting cases is if I trace out either Alice or Dave, and this is symmetric. So let's just take one example. Let's assume I trace out Alice, and our signaling means that the correlation between Bob, Charlie, and Dave depends on which measurement, so which parameter Alice has used. Now parameter dependence depends on Alice's parameter, which correlation the three others, Bob, Charlie, and Dave, share. Okay? But the correlation they share, by communicating at the speed of light, Dave at this point in time knows all the results, all the inputs and outputs. So at this point in time, Dave knows the BCD correlation. And so if the BCD correlation depends on Alice's parameter, this is faster than light communication, because you see it comes before that. And actually you could make this distance much larger by putting Alice much further to the left. So you can really see here that this technical parameter dependence can be turned into faster than light communication at the level of just the classical statistics of the inputs and outputs. So inputs and outputs are classical variables, and the statistics of these classical variables would be enough for, in this case, Alice to communicate faster than the speed of light to Dave. So if you don't believe in faster than light communication, you have here a problem. Okay, so that's what I said before. So this is now saying that you have a contradiction with the no faster than light communication hypothesis or statement by relativity, and so in this sense you also falsify this kind of explanation. So both the common cause and the direct cause are falsified, and so nature doesn't satisfy the principle of continuity, and nature is not local in this sense. So this is a negative statement. It is a negative statement because all what I did so far is to tell you how it cannot work. Now it's like Bell inequality. Bell inequality is interesting, but actually it's a negative statement. It tells you common cause doesn't work. It was an explanation for quantum correlations. Now I tell you, even if you augment common causes with direct causes propagating at a faster than light speed, but still a finite speed, it still doesn't provide an explanation. So maybe you have to go to retrocausation or to multiverse or to whatever. But certainly it leaves a lot of questions open. And so somehow, for instance, one kind of question which I find is interesting is how does an event A know that it is non-locally correlated to another event B? And who keeps track of who is entangled with whom? You know, this entanglement is usually represented in these enormous Hilbert spaces, and so are there angels manipulating these Hilbert spaces out there to make sure that the correlations happen in three-dimensional space the way they happen? Is entanglement somewhere written in our space-time, in 3 dimension? I think these are interesting questions, and I have only questions here, no answer. Okay, maybe one thing that's okay, because I try to see where could all this lead, and if you go to multi-party non-locality, so you have the idea of, okay, of course, if you have more than 2 parties, you can still have non-locality, but you could now say, are all my 4, let's say 4 parties really, are they all non-locally correlated, or maybe it's only these 2 are non-locally correlated and the 2 others are just spectators. So for that you can have this idea introduced by Svetlichny of being really fully non-local. And maybe a more relevant concept would be this non-signaling Svetlichny inequalities. And I think in this paper, Jonathan, you are co-author, no? Yeah. So I think this is a good motivation for this non-signaling Svetlichny thing. Okay, let's come to the conclusion of this. A violation of this inequality, well, implies either a violation of the principle of continuity, so non-locality, or it implies the possibility of faster finite communication at the level of classical measurement settings and results, so at the level of the statistics of the classical variables. And I think that both alternatives are about equally hard to swallow. I guess most of physicists would go for that one and give up locality. But actually, maybe this one should also be considered seriously, especially that if you have faster finite communication, but in only one privileged universal reference frame, this kind of faster finite communication does not lead to the usual grandfather paradox. You know, the grandfather paradox is the usual argument against faster finite communication. But if you have faster finite in one privileged reference frame, not in all of them, but only in one, then you don't have this grandfather paradox. So actually, maybe this is still a possible explanation. But then you have to accept, of course, that you can communicate faster than the speed of light. Okay, so how to tell a consistent story about quantum non-locality? Okay, in this book, and here I'm making some self-advertisement, this book is coming out in a few weeks. In English, it's already out in French. I'm trying to tell the story for the grand public, so we have something like a random event that can manifest itself at several locations. So that's the best I can tell you about how I see these quantum non-local correlations, but I wouldn't claim that I'm completely satisfied with this kind of statement, but at some point you have to write something down. Okay, thank you very much.